So what does recursion mean? It is a function that invokes itself, and it has a base case where it's going to stop calling itself. Because if it didn't have a base case like this one, if we have this function where we are calling it and we are passing it a number inside this function, if we didn't have any case here, it will keep calling itself forever. It's like an infinite loop. And so if we pass in a number in that function and we check that number if it's 5, then we keep minimizing that number into a smaller one. And then when it reaches 0, it will return the last number it was in. So it will return 0. In this case, we can see it how it's working. When we first start, it's 5, and then we can see it now it's 5. It will call itself recursive 5 minus 1, which is 4. And then after that, it checks if it's smaller than 1, then it continues and call itself now recursive n minus 1 is a 3, and now n is a 3, and then it continues until it reaches 0. And when we reach the base case, it doesn't exactly return n. Now you can see we have reached the base case, and now you will see that first the stack is like reversing. So it's doing a stack unwinding. It's getting popped from the call stack. And each call is storing the data that the function has stored inside it. And then when it hits the base case, it will pop the stack frames in reverse order. And then it will print the result, which is 0. Here you can see it's building up until we reach the base case. When we reach the base case, it will now reverse the order of the function call. And then it prints the result of the return. And recursion doesn't replace while or for loops. It breaks down problems into sub-problems, and then it combines the results. And it is mostly useful when deleting folders or files inside or folders inside folders when we have a tree. And it is also useful when deleting nodes inside nodes. It would make the code simpler. And you can see it in Windows, where we delete something recursively in command prompt, where you can enter in the command prompt in Windows. You can enter this command where it deletes a certain folder and everything. And you can even see it in Git when you write a command in Git rm, and then you pass in -r, which means recursive, to remove a directory and all its content. We will create a recursive is palindrome function where it's gonna check if a word is palindrome. We should start by defining a function called is palindrome, and then we pass in the word as a parameter, and then we check if the length of that word is less or equals to 1. Then we return true if that's the case. Else if the index 0 of the word, which is the first character in the word, is not equals to the last character inside the word. So we just check it by taking the length of the string and then decrementing by 1. And then if that's the case, then we return false. And then at the end, we return the recursive call, which is gonna be is palindrome. And we are gonna take the word and then the index starting from 1 to the length of the word and then -1. And now let's try and run the program. That's true. Wow is true. Word, whatever it is. And now you can see that the print is not really. Let's make it prettier and use another word like I. And yeah, that's how recursive is palindrome function works. And let's debug the program and see what happens inside. We first check if the length of the word is smaller or equals to 1. And then if not, we will say the word 0 is not equals to the last letter. So the first letter is not equals to the last letter. And that's gonna, if you think about it, all palindrome words have the same start and ending. So it's a smart way to just suss it out if the first character is not equals to the last character in the string. And then if it's not, we are gonna recursively call the function. And now we'll end up with only one character, and so it will go inside the true because we have skipped the first character and we have skipped the last one. So now we end up with only one character, and if it's smaller or equals to 1, we will return true. And if we make it even longer, we can see what's happening again. We can see that it's gonna check if they are equal to the first and the last, like we said. And if not, it will slice the string it will remove the first and last character. So now we end up with the characters in between them. So N, and then it's gonna check if they are equal, and if they are, so we are going to recursively call the function again. And we will also remove the first and last character. And now we can see that we have 2 characters and they are equal. So now we recursively call it again, and now we have 0 character, which means we return true. And that's what happens. It just rejects that word if the first and last character aren't equal, and we just return false. And then if we have the same, let's say we have the same thing, but it's not not actually equal. And it's gonna do the same thing, it's just gonna do it in one more recursive call. So now we reach this recursive call and it's gonna remove the first and last character. And now we have n and t, and it's gonna compare them and they are not equal, so we return false. And that's how everything is working in this palindrome recursive function. And to make the code slightly more readable, we can replace the length of the word by word length, then enter len word. And now we can replace all those by just word len. And now it's a bit more readable, maybe, because we have it here, so we don't need to calculate the length of the word each time we run the program. Each time we check a condition, it just counts it once, calculates the length of the string once, and then we check it here. We use that variable here or there. It works the same way. And it should work just about the same. No. Did you know that the previous isPalindrome function is not very efficient because it creates a new string for every recursive call? And to avoid creating new strings, we can use the low and high parameters, and we can use a helper function, which is called a recursive helper function, to make it more efficient. So if we start by declaring a function called isPalindrome helper, and it will take the word and then low and then high, and then we check if low is bigger or equals high, we return true. And then we check if the word, and we check the index, which is the low, not equals word high, then we return false, and it should be else if. And then we return palindrome helper function again, and we pass in the word, and then we increase low by 1 and we decrement high by 1, and therefore we have it like that. And then we should create a isPalindrome function which calls the palindrome function helper, and then we pass in inside it the word, and then the low is 0 obviously, which is the first index of the string, and then the high is the length of that string and -1. And now we have this recursive function which has a recursive helper function. Now let's try and run the program to see what happens. Yeah, and we should return it. I forgot to return the function call, so now I didn't receive the right result. So now let's run it again. And as you can see that we have this one is false, which is correct, false also correct, and this one is palindrome, which is true. That's how recursive function helper works. Just a function that calls another recursive function. Selection sort is finding the smallest element in the list and swap it to the front, and then recursively sort the remaining list, ignoring the front element. And now we will write a helper sort function for the selection sort, and we start by first writing an if statement. If high is bigger than low, then we should keep track of the minimum index, and then we should access the minimum number or the number at the start of the list, and we do that by just accessing the low index of that list. And then we start a for loop for I in range low +1 to high, and then we keep track of the current number inside that for loop, and we access it by using the I index of that list, the current index in this for loop. And then we check if the current number is smaller than the minimum number, the number we started with in the function. If it is, then we should update the minimum number to that number. So we say that minimum number is current number, and then minimum index to I. And now we have updated the minimum index of that number. And now we need to do a swap. Assign list minimum index to list low, and then list low equals minimum number. And now we have done a swap, and then after that we should call the sort helper again recursively and pass in the list and increase low by 1, and we pass in high. And now everything is working correctly. As you can see, I have passed in the list, this one, and we try the first one again. And as you can see, it has been sorted as well. And in the sort function where we call it, we should pass in the list and the first index for the low, and the high is the length of that list. And everything will be working fine. Let's debug it and look at it more deeply, see if we can see something interesting. So now we have passed the list, we call that function, and we also call this helper. And inside the helper function, we have high as 7, which is the length of that list, 7 element list. list and the low is 0. And first we have the minimum index as 0 and the minimum number as 5. It should be minimum number is 5, yes. And in the range we have low plus 1, which is 1 from 1 to 7, so 1 to 6 basically. So now we are in the current number, which is 4. So it's gonna see if 4 is smaller than 5. Then we assign that minimum number to the current one because we found a smaller element and we save the index of it. Then we check again and see if there is any smaller element than 4. We check the index 2, which is 1, and it's gonna check if it's smaller than 4, which is it is, and it's gonna update the minimum number with that number. And now minimum number is 1 and the index of it is 2. Yeah, it's 2. And then we check if the next element if is smaller than 1. It's not, so we just loop again. Check if 2, no, it's not. Basically 1 is the smallest one, so it's gonna skip everything and it's gonna loop through the whole list and check if it's smaller, and it's not gonna see that smaller. And then after that we're gonna hop into this line where we have the list of the element in the minimum index, which is 2. So 1, we are just updating its value to the list low, which means the 5. So now we are swapping 5 with 1, and here we are swapping back the 1 to 5. So we're just updating the first index of that list to number 1 because it's the smallest one. And it's gonna do that until we reach the final destination. It's gonna do the whole loop again, and it's gonna see like now starting from the index 2, and it's gonna see if 5 or 7 or 2 is smaller than 4, and it's gonna do the whole process again. And that's how everything is working. It's gonna keep swapping them, and yeah, I think you get it. Yeah, it's gonna recursively call the function and increase low by 1 until I becomes equals to low. Then it's gonna stop. And yeah, that's how the helper selection sort is working. A Fibonacci sequence is a series of numbers where the next one is the sum of the two preceding ones. Like this here, like in this picture, we can see that 1 plus 1 equals 2, and 1 plus 2 equals 3, and 2 plus 3 equals 5, and 3 plus 5 equals 8. That's what the Fibonacci sequence is. But how do we calculate the Fibonacci of a certain number? We first have to create a function called Fibonacci, and then we enter index. Then we check if index is 0, we return 0, and if index is 1, then we return 1, and then we return the Fibonacci sequence, which is the recursive call of the Fibonacci function. We first decrement by 1 for the first sequence, and then we sum it with the recursive call of the preceding number of the last one, so the -2. And then when we calculate it, and as you can see that the result was correct, the sum of the Fibonacci sequence of the number 9 is 34. And when we say that we want to calculate f9 as an example, what we are actually doing is if we have like this function where we have fn minus 1 plus fn minus 2, so we get f8 plus f7. And what f8 means, it doesn't mean that you are calculating every single number before, like 7 plus 6. That's not how f8 is calculated. f8 equals f8 minus 1 plus f8 minus 2. So f8 equals f7 plus f6. And the same for f7. f7 is f6 plus f5. And here we have an easy table to see where we can see that how it is calculated. We can see that f7 equals 8 plus 5, which means 13. And f8 equals 13 plus 8, so 21. And so this is how we got this to the solution. We are not really adding up all those numbers behind it when we say that we want to get f8. We're not calculating, if we're not adding 5 and 3 and then say, okay, this is the Fibonacci sum of 8. We are actually calculating f8, which means f7 plus f6. And then you have to calculate from the start. Okay, let's see how the code is working. So first we get a function, and now we will start and see how the code is working. And as you can see, the first function gets called, or the first recursive call is getting called until it reaches 1. Then when it's 1, it will return number 1, and we will go back to the index before it is number 2. And then after we return the number 1, we go to the second recursive call, which is the -2, index -2. And since we have 2, so basically what that means is on this current one, we will have index equals it will be Fibonacci 0, and when it's 0, it's going to return 0. And since we have this one as 0, and then we have the last one we calculate here 1, that means f2 equals 1, just Fibonacci number 2 equals 1. And that's it will be saved in the function called function stack memory. And as you can see here you can see that the return value is 1 for index number 2 for Fibonacci 2. And now we will go back to the number 3, and you should notice that we are going back in calls. We're not starting from 9 on the second recursive call. So now we are going back, reversing to the number 9 from 2 to 9. Let's say you are in university right now and you have an assignment to write a recursive factorial function to calculate the factorial of a given number. We start by defining a factorial function that takes n, and then we know that in mathematics that the factorial of 0 and 1 is 1, so we check if n equals 0 or n equals 1, and then we return 1. So we need to return n multiplied by factorial of n minus 1. And now when we call factorial, we get, let's call it for 0 and then call it for 1 and 5, and then we print the result and let's see the answer. And we have them right here. We get 1 for 0 and 1 for 1 and 5. We get 120, which is correct. Now what's happening actually inside? Just like before, I did a video on recursive function. It's very similar, only that we are just multiplying by n. That's the difference. And we are adding this n0 or 1. And both the first calls are easy to understand. It's nothing. And now here you can see that we are multiplying n by factorial n minus 1, but actually we aren't multiplying anything at the moment because you can't multiply n by a number by a function. So now it's only calling the function. As we can see here on the side, you can see it's only calling the function and decrementing n by 1, and we only get like that. Now we reach the condition 1, and now we return 1, and now we multiply n by 1. We have 2, and here we multiply 3 by 2, which is 6, and here we multiply 4 by 6, which is 24, and now we multiply 5 by 24, and now we get 120. That's how it's working. It's a bit confusing, but that's how it's actually working. And we call the factorial function and we pass in 5. What happens? First we have a check whether it's 0 or 1, and then we return 1 if it's 1 or 0. So now when we call function factorial 5, what does it equal to? Factorial 5 equals n, which is 5 multiplied by factorial 5 minus 1, which means 4 basically. Okay, so the program would say, after calling it, the program will write down, okay, 5 multiplied by calling the function 4, factorial 4, and then the program will call factorial 4 equals 4 multiplied by factorial 3, because 4 minus 1 equals 3, so 3. And then the program will take this one and write it here, factorial 3 equals 3 multiplied by factorial 2. Okay, 2 is not, we have not reached the base case, which is 0 or 1. In this case, it's going to be 1, because we're not going to reach 0. Okay, we call now factorial 2 equals 2 multiplied by factorial 1. And now what we know so far, we have reached the base case, which is factorial 1. And now factorial 1 equals 1. And that's what we know so far. So the program, after reaching the base case, will now unwind the stack. And what basically means now we are going back in calls. This one will become 1, the factorial 1, on the previous stack. And this is the stack, basically. This is the stack calls that we have called. And it's gonna be first in, last out. So the first one it enters, which is this one, it's going to be the last one getting released. So now the program is going back in calls and it's calculating factorial 2, because now the program knows that factorial 1 equals 1. So now factorial 2 equals 2, because 2 multiplied by 1 equals 2. And now, since we know factorial 2, we go back to factorial 3, and we know that factorial 2 equals 2, and now 3 multiplied by 2 equals 6. And since we know factorial 3, so we go back there, factorial 4, and we see that 4 multiplied by factorial 3 equals 6, and now 4 multiplied by 6 is 24. And since we know that as well, we know factorial 4 is 24, we have it here that factorial 4 equals 24, and 24 multiplied by 5 equals 120, and that's the result, the last result we get from the factorial, and that's how the program is working basically. Alright, we have recursive binary search, and what happens in recursive binary search is that first we create a function that calls a helper function, and in that function, as we have done before, for. So in this function, we pass in the list and the key we are looking for inside the list. And then we call that function and we pass in the low, which is the first element in the list, and the end, which is high, the last index inside the list. And then we create a helper function. And now we check first if low is bigger than high, which means that we haven't found anything, so we just return not found. And now we need to find the mid element, which is low plus high combined, and then double forward slash and then 2, which means that they are divided by 2 and they will give us an integer. I think it's called the floor division. And now we will see that if the key is smaller than the list mid. So now we are accessing the mid of the list, and we're gonna see if the key that we are looking for is smaller than the middle element inside the list. So if it is, then we just recursively call the helper function again, and we pass in the list and low and mid -1. So now we're gonna look on the left side of the list, since we have divided it into 2 parts. And then we're gonna see if the key, maybe the key equals the mid, the element in the middle. Then we just call it like that and we return mid. Else we return now the right side. We look for the key in the right side of the list. So now we just call the recursive helper function again and we pass in list, and now we should, in the low side, we should just pass in mid +1 and then high and then the key we are looking for. And now the job is done, basically. That's what we are basically doing, is that we are dividing the list into 2 parts, which is left side and right side. And the list must be sorted from the start. Otherwise, the binary search will not work if the list is not sorted. And now we are sorting the list here and we are printing the sorted list, and then we are checking where the index that we have found the number in. And now let's run the program and see for what's going on. And now we can see that we have found the number 7 at index 5, since we have passed in 7 here and we passed in the sorted list. So what we are basically looking for is the number 7, and after it was sorted, the 7 was at the end of the list. 1, 2, 3, 4, 5, 6, -1, so 5, yes. We found it at index 5, and now if we look for number 2, we are going to find it at index 1. And now we look for something that doesn't exist, let's say 8. And here we get not found. Here we have an example where using recursion is actually easier than solving it not using recursion. In this example, we are going to use recursion to calculate the size of a certain path. It's going to be similar where we recursively deleted a certain path. And now we start by declaring a function called getSize, and we pass in path as a parameter. And now we have to declare a size variable called 0. We assign it to 0. After declaring the size, we have to check if the current path we are in is not a file. We have to write if not os.path.isFile. And now we will list the directories inside. And we're going to use os.list directory. And we pass in the path. And then we start a for loop to explore the subdirectories inside each directory for subdirectory in list directory. We increment the size by the recursive call of that function, where we pass in the path and double backward slash and the subdirectory. And we should have a case where we don't have a directory, just a file. So we just calculate the size by doing plus equals and then os.path.getSize. And now we pass in the path, and then at the end of everything, we will return the size. And now let's run the program and see what. And I forgot to pass in the path here. So now we have it correctly set up. And now let's calculate the size of the exercises directory. And it says that it is 1 megabyte 0.393. And it says here it's 1.32. It's a bit different, but it's not that difference. If we calculate it in bytes, we're gonna see that it's 139383183. It's almost the same on the Windows part where we can see it here. This is how we calculate the size of a certain path using a recursive function. What if I told you this entire fractal comes from just one triangle and a couple of lines of Python? This is called the Sierpinski Triangle. It's a mathematical fractal. It looks complex, but the rule behind it is very simple. It is just the same triangle gets repeated. These 3 points define a triangle, and to draw it we connect them like this, P1 to P2 to P3. And to connect them we draw P1 to P2 to P3 and then P3 to P1. And why is this useful? This idea is used everywhere. It's used used in game engines, OpenGL and Vulkan, and 3D models and physics meshes. Modern graphics are built almost entirely from triangles. In this video, I'll show you how to generate a Sierpinski triangle using Python and tkinter. We will go through recursion, geometry, and how a simple algorithm can create a complex fractal. A Sierpinski triangle is a mathematical fractal. It's created by repeatedly subdividing a triangle into smaller triangles. At each step, we split the triangle into smaller triangles, so the higher number of steps, the more triangles you will subdivide. And this makes it a perfect example to understand recursion and divide and conquer algorithms. So this program uses tkinter for the graphical window that you have just seen, and it uses recursion to generate a fractal, and it uses geometry to calculate midpoints. The user enters an order which controls how many recursive steps the triangle has. First, we start by creating a tkinter window and a canvas, and we name that window Sierpinski Triangle, and the canvas is where we draw the triangle, and we define the size of it and we pack it into the window, and then the user can choose the recursion depth by entering a number, and we capture that number here using self.order, and we add a label, and then we add an entry field, an input field, which takes the order of how many subdivisions we want to make. A button is just to confirm the input that we have entered, and we have a main loop for the window, and this makes it easy for us to experiment with different numbers. So first, when we start the program and click on the button, we are going to call this function that first deletes the canvas, deletes everything, and then we define the points for the triangle, which is P1, P2, P3, and this one is the one containing all the fractals inside. So this is the biggest triangle outside of everything else. This is the one right here, and those are fractals. And display triangles is the main function that we should focus on, because this is where we are doing the recursive call. If the order is 0, then we draw the line P1, P2, and this is the base case, to simply draw the line for the triangle. So when we first start a function, at the start, if the order is not 0, then we're gonna have to calculate the midpoints of each line in the triangle by using the function midpoint. And inside the function midpoint, we are creating a list of 2 elements, and then we are calculating the length between the point 1 and point 2. We are incrementing them together. We are calculating the total of them and then dividing the total by 2. And on the second point, we are calculating the length between point 1 and point 2 and dividing them by 2, dividing the total by 2. And then we are returning this array, which is the midpoint. And so as you can see here, if we calculate the points in between 2 points, we get a midpoint of each line in the triangle. So we have P12 here and P31 here and P23 here. And then we are going to draw the line connecting them together. And if we do that, we are going to get another triangle. So when we pass in this one, P31 and P23, P31 and P23, we are going to get this triangle. We are going to get this triangle, and when we print and when we recursively call the display triangle, we are going to get P31, P12, and P1. And we minimize the order, and then we also print this part right here. We recursively call the third one, and this is the order if the order is 1. So for each triangle, we are going to get like a bunch of triangles inside, and you can do that until the program crashes. And the higher the number, the program takes a lot of time to finish drawing the whole triangle, all of the triangles, and then the window stops responding. And this is where we draw the line between the points, and we have 4 points, each one we are connecting them together. We have a classical recursion problem called the Tower of Hanoi, and in this game, these rings, you have to move them from this tower to the third one, and you can't really move them like from the bottom up. You should move them exactly like this, and you cannot place a larger disk on top of the other. And now you will see that, so we start by moving this one here and this one here, and then we move back this one, and now we move this one there, and we can move the smallest one back, and then we move this one here and then this one here. And now we have 7 steps. We have done it in 7 moves, and programmatically we can solve it using recursion if we have 3 towers, and we can move n amount of disks using a recursive function to move them from tower A to tower B using tower C as an auxiliary. And the rules of the game is that only one disk can be moved at a time. Larger disk can never be placed on a smaller disk. All disks start on tower A must move the top disk only. And now let's start implementing it by declaring a function move disks, and it will take n, and it will take from tower and to tower and auxiliary tower. And we have a base case. We start with if n equals 1, and we print move disk n from tower to tower, and now we have else and we call the recursive function where we pass in n-1. And now at the start we should, like we did before, we should move, if we think about it, from tower should be the from tower, and the to tower should be the to tower, and the auxiliary tower. Well, in this one we are moving them from A to C. So to do that effectively is that we need to do it this way. We should move them first. The first one we should move it to the destination. But if it was B, then we should do it differently. We should move it first to the B, which is the destination, and then we put this one on top of this one. So now if we think about it programmatically, is that, so the first step is that we have, which one is the auxiliary? We choose the destination one as the auxiliary. Yeah, because now we are using this one as an auxiliary. Now we have to move it there. So we have B as the auxiliary at the first step. Okay, so we start from tower, and then the auxiliary is the to tower. So to tower is auxiliary tower, and obviously the auxiliary tower is the to tower. Yeah, exactly. This is correct. And now we have it like this, just formatted it differently. And now we print move disk and basically copy and paste the other one there. So if you copy it and paste it, we just have it like this, so we can move it. We can see it when we run the program. And now in the second step, what are we doing? Well, since I moved, this one is the first step. The first step is actually moving from tower to the auxiliary, and then the auxiliary tower to tower. The second step is that we move this one right here. So that means we are moving from to auxiliary tower. So now move disks and n-1, and then from tower is the auxiliary tower, and then the to tower is to tower, and then auxiliary tower is the from tower. Let's run the program and see how it's works. Now we have the auxiliary tower as C. So when n equals 3, it will not go inside this part. So when n equals 2, it will move to the second step. It will move to B. So this one is the first step, and this one is second step. So we will move disk 2 from A to C, which is correct, A, B, C. And in the secondary recursive call, n is going to be equal to 2, and we are going to move disk 1 from B to C. So now we move this one right here. And then we are in n equals 3 in the secondary recursive call, and we are going to move disk 3, which is this one, from A to B. And then we have to move disk 1 from C to A, so there. And then the disk 2 from C to B. And then at the end we move disk 1 from A to B, and which is correct. This is how we move the disks from tower A to B using C as an auxiliary. And what if we want to move them to C? To be able to move to the tower C, we only need to switch this one to C and the other one to B. So now we are passing in as the destination is C. So now we just if we run the program, we will see how we will move the disk 1, we move it to C, and then move disk 2 to B, and like in the steps we have seen before. Now I'm gonna wrap everything up in recursion. Recursion is just an alternative way of doing loops without using the usual ones, which are the while or for loops as an example. So in this example, we can see that we are doing the factorial in the iterative way. And in the iterative way, we are just using a for loop. And compared to the recursive one, we are using the recursive function, which is we are calling the function again, and we have a base case to stop the recursive function from keep calling itself again and again and again. Recursive functions aren't as efficient when it comes to memory and time complexity. Each time we call the recursive function, the program will allocate memory for the function variables and parameters, and it will consume a lot of memory, and it will take extra time to manage the additional memory. And that's why iterative solution is always more efficient, and any problem that can be solved using recursion can be solved using iteration. But it could be more difficult because it depends on the nature of that problem. For calculating the directory size and for recursively deleting a directory, using recursion is more intuitive. It provides a simpler solution than using iteration. So should you use recursion or iteration? Well, it depends on the problem. You should evaluate whether it's better to use recursion. In your case, it depends on you want to have you really care about performance and memory, then recursion is probably not the greatest idea. Also, recursive programs has a risk of running out of memory, and it will cause a stack overflow. There's something called tail recursive function, and tail recursive functions has no operations after the recursive call. So in this one, we see that there's no operation after it because we are calling it here and then it keeps calling itself without doing any operation afterwards inside the function. Meanwhile, here we can see that we are multiplying after the recursive call. And a tail recursive function is more efficient for reducing the stack size. Some other compilers will optimize tail recursion to reduce the stack size, but Python doesn't support optimization of tail recursion.